I work for ENEA, and as a large public institution in Italy, and I have been the coordinator of NEXTTOWER. NEXTTOWER is a project that is over, is done. So this is going to be a walk through the project and the results, the approach, and let's say the outreach after the project. In fact, as the title suggests, I'm going to give you an example to the SISAL-SLAG project, which is still ongoing. Of course, I speak on behalf of the entire consortium, and in terms of facts and figures, NEXTTOWER was a medium-sized project, 5 million of EU funding. It's been, however, brought forward by a relatively large consortium, 18 partners, so a big crowd. And the ambition was to develop a kit of innovative materials for next generation concentrated solar power tower system, the one working with atmospheric type receivers. We wanted to demonstrate this material set to work at 700, 800 Celsius and bring it to TRL7. But the real meaning of this proposal was really to try to shorten the development cycle of this type of materials down to 4 years, which is extremely important. And as Peter said this morning, somebody from Alfa Laval, the representative from Alfa Laval, really brought this aspect forward with the issue of developing new materials. And it was striking because, of course, we are totally in line with that. So at a glance, this was the distribution of the partners recruited for this job. And of course, there is a big contribution also from Sweden. KTH and Sandvik were prime partners in this consortium. However, we really brought together industries, RTD centers. There was UNE, so a standardization body inside the consortium, and Certimac, a notified body in the consortium. I'll tell you why this was important. So when we let's look at the context. When we look at the concentrated solar power, we have several type of systems, from parabolic dish all the way to parabolic trough, and we focused on central receivers. They all have different technological challenges. Solar tower were systems, or have been systems, suffering from some limitation in the reliability of the solar receivers. This was the basic fundamental challenge we wanted to address. But when you talk about concentrated solar power, you have something that at the same time ideally could work at much higher temperature than what we are currently doing, right? So we are bound at about 550 Celsius of the storage module. And you cannot really go much higher in the receiver compartment unless you re-engineer downstream also the storage block to manage higher temperature heat, right? So, and when you go up, you encounter harsh conditions, and you have to face carbonizing atmospheres, erosions, corrosions, this type of problems. So what was our approach? Is really to develop a new class of materials that are cost-effective and could bring higher performance, or at least higher reliability. Even achieving higher reliability would do the job in certain cases. So a tower system looks like this. This is a tower system at the Plataforma Solare de Almería, one of our partners, CIEMAT, in Spain. And you can see on top of this tower there is the higher level receiver, which is made of a support where containing a number of small tiles, 20 by 20 centimeters tile, connected in parallel and covering an area of several square meters. This tower is 80 meters high, and we have installed our receivers at one of its level. I think it was a 53, 56 meters high. Again, we are working on the receiver, but it's also we're scratching the surface. We have to engineer downstream the entire concept to make it work. Please. If we are looking at the relatively low temperature paradigm that we are exploiting today commercially, molten salt technology is the storage block system that we are exploiting. 550 Celsius is coupled with a steam generator, and then you can go and power a steam turbine. Okay, we are now changing the receiver, and we are trying to develop a high temperature concept. In our idea, we try to use liquid lead from nuclear, borrowed, mutuated from liquid lead coolant type of application for Gen 4 fission systems. And these allow us to go well above 550 because it's stable at 700, 800, and even above. So it's a good heat transfer fluid and heat storage fluid in principle. Of course, you have to face the challenges associated to liquid lead corrosions, which are substantial towards any of the current steels available in the market. However, if you do that, then you can think of coupling this system with a Brighton gas turbine, Brighton cycle, and you can use now this type of high-quality heat to power process industry. But our focus is again on the receiver and the storage block. This was the scope of NEXTTOWER. Through this scheme, let me explain you what we did. So we used an existing heliostat field. So the mirrors were there. We used the same tower. We just put new receivers on top of it to try the reliability compared to the first generation. So we had the design, we have the geometry. We wanted to use we re-engineered the SOL-AIR from 2003, SOL-AIR receiver, into something more reliable, more performing. And then instead we completely re-engineered and went from developing base materials all the way to building a full-size prototype for the liquid lead single vessel storage module. The objectives then were essentially three. So more durable receivers, able to work for more than 20 years at higher temperature, maintenance-free. This was the request from the European Commission. It was set in the call. But then we want also to bring new class of alloys, some ferritic alloy called Fecral by Cantal, Sandvik. And in the end, we wanted to demonstrate them in the field. And so we developed a SOLED demonstrator. SOLED is the name of the demonstrator. And we had to split it. One was developed, SOLED 1, in Spain for the solar receiver, and the other part, SOLED 2, in ENEA for testing the liquid lead storage module. So as far as the ceramics materials are concerned, these are the receivers that we engineered. And we went from testing several types of design, working with different types of lattices, try to see what would make sense, so small pieces, before building all of the entire, I wonder if this works, yeah, the entire solar receiver cap, which looks like this. And then they were mounted on the top. But in this type of project, we have to really pay attention to the manufacturing process. These materials, we wanted materials that were new, innovative, but could be manufactured and ready to be brought to the market right after the project. So this, for example, was the process developed by one of our partners, Lictech, Denmark, to actually create the final full-scale production of this type of receiver, which was an innovative all-SiC silicon carbide design that was processed at temperatures above 2000 Celsius and was basically endowed with much less defectivity compared to the former receivers from 2003. Please, let's go ahead. But we didn't really bet on one design. We wanted to make sure to deliver something to the European Commission, to the community, so we challenged two companies, Lictech and GCR, to design two different receivers. And they are different because they are complementary. They are not really one against each other. One has a strength in the robustness and able to be, their ability to be pushed in terms of temperature of operation. The other one is created by 3D printing, adds flexibility, is optimized for fluid thermal performances, and can reduce losses. This is a picture of how they were mounted. I think we mounted 50 and 50, and we ran in parallel. Please go ahead. But even achieving good performance, no failure, so our tests so far are good, and we are pretty happy about it. And developing 2 prototypes, each one with its own merits. The importance of having standards was recognized upfront. There was, I mean, this would have been a much less result than if we didn't achieve also a job done in standardization. And I'll tell you what I'm talking about. Please go ahead. We contributed with a task force inside NEXTOWER to the revision of an ISO 18755 on fine ceramics. But more importantly, we have developed a SEN workshop agreement, which is called CWA. And this was Peter was probably hinting before, because last year the European Commission issued some standardization booster and some guidelines based on best practices. We also contributed some of our experience from this project. And this is now something that has been brought to the attention because it's feasible within the scope of a European project usually. This is important because if you have something like this, which is a pre-standardization document, when you have results, the uptake from the industry is going to be much faster. And all the companies, all the industry in your consortia, in our consortia, will benefit from it. And this is important to reinforce the material leadership of Europe. Please go ahead. So, in fact, quite unexpectedly in 2020, we won, we received, the award from the Innovation and Standard from SENELEC. And this was just a confirmation that our initial approach in 2016-17 was convergent with a request from the community, from the European Commission, because it was a bet. We tried to build in the possibility to create and cover gaps in standardization by designing our consortium with some standardization capability inside. And in any case, we also, during the management, we created a task force on standardization. This is a subgroup of people that cooperate on that, just to make sure that we wouldn't lose track of standardization while focusing on technological developments. Please go ahead. But ceramics were one part of the development. The other part of the technological development dealt with the creation of the storage module. So we started from scratch. We went from Kalfa type of simulation, so really thermodynamic design of materials and rational design of this new alloy. We identified an area of feasibility where the materials would be ductile enough to be put in place and weldable, because of course we wanted to create a new alloy to be used not as a structural material, but as a functional material, okay? So as a coating. So it needed to be used as a cladding or as overlay welding. And so you design usually the property as a bulk material, but then you have to think that you are not going to use it as a bulk. The idea of this new material is that it contains some aluminum and it possesses some self-healing properties because it creates a nano layer of alumina which self-passivates and protects the material, from the essentially stops the corrosion from liquid lead at those temperatures. Usually what happens with liquid lead, it kills and leach out all the nickel out of superalloy stainless steel. And there is no current steel that can work with that type of liquid lead. This is the blocking factor. This factor stops that. It's an effective barrier. So please, just 1 second. Once we designed that, we tested it on small coupons, and we also tested with materials with defects, crevices, cracks, and we also tested in welded coupons for accelerated testing at 800 Celsius for several months. We went full scale, and we produced 10 tons batches with Sandvik. Please go ahead. And then again, we have to make sure and to optimize the welding procedure. Please go ahead. To make sure that we would be able to actually deploy this material, and we have to develop certified procedure to actually do this job. Please go ahead. And Sandvik was so involved into this project, and this is so important The involvement of industrial partners is absolutely fundamental to achieve ambitious results. That we actually had to develop several types of formats: wires, strips, rods for TIG, bulk tubes. There is much more than this. We don't have time to cover this. But without this, we couldn't run combinatorial experiment to see what was the best solution. Please go ahead. To actually produce this. This vessel is 3 meters high, is 35 tons, contain 35 tons of liquid lead for a total weight of about 50 tons. And you have to consider that the overlay job, the overlay welding, takes months and months, because you have to essentially deposit 10 kilometers of wire inside just the main vessel. And all the interiors of the vessels is made of fecral. So it's a full one piece of one-off component of brand new alloys in all its parts. So these are some of the pictures that show the making of this vessel. Some of them have been done through robots. Some of those are done by humans. Of course, there is the creation of the shell. So you have structural welding. And then you have the interior overlay welding to coat inside this vessel. Please go ahead. And of course, there are lots of instruments, a lot of things that go with it, because we want to run it unmanned, so without any operator nearby. And this was the design by ENEA. And of course, our nuclear experience from our nuclear engineers have come handy. Please go ahead. So finally, we installed it in our nuclear facility, which is a center of excellence for liquid lead in Europe. And in the end, it turned out to be the best facility towards this vessel. This is how it looks like in place before actually being covered with air conditioning system, because it's actively cooled. Please go ahead. But what is the problem now? We have technical develops in ceramics, in metals, and of course, you can be more or less successful. It's always a gamble. You never know whether you'll be able to reach your objective, or what type of unforeseen problems you will face. But the idea is really that we have tried to show that shortening the development of material is possible, as possible. Please go ahead. Several activities worldwide, like Mission Innovation, which is a high-level initiative between governments worldwide, had already identified, as this morning our speaker pointed out, that the shortening of the material cycle from 20, 15, 10 years is a bottleneck for innovation, and is absolutely one of the steps we need to focus to actually address the Green Deal, circular economy. And what we try to do with NEXTOWER is to see, let's see whether we can bring this 10 years down to 4, okay? Please go ahead. And of course you do, in this picture, you have a schematics representation of all we have done, okay? So we started from materials, then we went through lab scale, demonstrated, scale up, and launch operation, commission the entire plant. And if you do this, please go ahead, and you want to reach the market, you need to use standardization, okay? This is absolutely fundamental. In some cases, we did it for the ceramics. In other cases, we weren't able because the gap was too much, was too broad. But again, this is something that now, for example, would be able to push better with an extra effort now that we have this first experience on liquid lead. Consider liquid lead was completely one-off. It has not been used at this temperature, neither in nuclear, nor in any other energy field and CSP. So it was radically new. So the impact is cross-cutting across the industry, okay? But I'd like to point out, please go ahead, the possibility of using this type of technologies for CO2 looping. This is a beam down plant credit from Magaldi, and also try to couple this type of improvements with CO2 power cycles. As a matter of fact, I'd like to end my talk showing the convergence between NEXTTOWER and another project from the European Commission, which called SISAL pilot. We met with the coordinator from the SISAL pilot project at the time, was midway through NEXTTOWER. We said, how can we do things together? And we decided that we could actually add an energy harvesting module to the original concept of the SISAL pilot to actually create something that goes towards the recycling of silicon. As a matter of fact, this is a project led by Norway, which is one of the partners that you mentioned is involved in photovoltaics industry, and they have is a hot spot in Europe for this type of technology, and also for the production of high purity alumina. Please go ahead. The idea is, if the original project has this type of schematics, we said, let's develop just an energy harvesting module in this point of the plant where we are trying to take calcium carbonate and split it using some power or any other, maybe even electricity, if we have extra, to actually power 700, 900 Celsius cycle to split calcium carbonate and have calcium oxide on one hand and capture of carbon dioxide. And this is effectively a chemical storage. So we are storing energy in a chemical form in these two components, and we can recombine them to have an exothermal reaction when we need it, on demand. But again, we created a work package 6. You can take this, you can go and look at the website of this project, and this is taken from there, where we try really to make the link between NEXTTOWER and this SISAL project. And with a practical approach from NEXTTOWER, we are delivering, I think these are the months, that type of demonstrator. Of course, it's a much smaller demonstrator, but again, the approach. We had technical objectives and market objectives. We never lost the track. We really believe that this is a viable approach for high TRL innovation action. Please go ahead. So, final remarks. As far as CSP is concerned and NEXTTOWER is concerned, we have developed a durable monolithic receiver as we wanted. We have also provided evidence that the liquid lead can be used in heat transfer fluid and heat storage fluid. And also, we have, in doing this, we have created a new alloy capable of working at high temperature in a harsh condition above 600 Celsius, so beyond molten salts. Please go ahead. In the end, more broadly, what we really think is that the developmental cycle of materials for energy harvesting can be shortened, and this is absolutely crucial. You can do this by including upfront all the stakeholders in the value chain, including the standardization actors. And essentially, I want to stress this fact. NEXTTOWER is a deep tech materials project. It's not a CSP project per se. It's not a component on architecture. It's a materials project. And this materials project can go a long way, even in high TRL innovation action. And I think this is something that is important to stress because materials are the current bottlenecks in many areas, in many revolutions. And with this, I think that with the support of the Regia, I like to thank the European Commission. All the project officers that supported us would have not been possible otherwise, and I'd like to thank you for your attention.
Thank you so much. A great insight into the challenges, opportunities in storing actually the energy we get, and bringing it to the market with an interesting aspect also how to accelerate the bringing up to the market. There is, before we come to the questions and when we harvest some questions, I want to make a publicity here. You mentioned the standardization booster. So if anyone here is involved in an EU-funded project and you come to the point where you think maybe it would be good, we could do something on standardization to bring it to a standardization. Contact the standardization booster. This is a project which will give you additional funding in order to bring in the right standardization organizations into that project. Standardization booster, and you get a bit of additional support to bring it to the market. So, harvesting questions and energy. We are
Gerhard Domann from Fraunhofer. So did you try out to use digital tools for acceleration of material development, and do you think there's a potential involved you want to capture in the future for that?
Excuse me, can you say what are you asking?
Digital tools for the material development, for the acceleration of material development. If you want to shorten the time to market scale for material development, then you can take use of digital tools, material data.
Materials, I mean, what we have done is using thermodynamic materials databases and Kalfa type of instrument, algorithms to actually screen out faster what out of the all possible combinations, you know, and composition, what would make sense. This was used for sure for the metallics, for the metal materials. I think it's absolutely fundamental.